Question 1. Assume U1 and U2 are open subsets of C. Show that the union U1 union U2 is open. Right. So I'll write down definitions in blue. So what does it mean to be an open subset of the complex plane? So definition, U subset of C is open if and only if for all, let's call it Z in U, there exists a radius R bigger than naught, such that the ball of radius R centered at Z. So what I mean by that, of course, is the set um, uh, the set W in C, such that, sorry, not very nice, but I'll go to the next line. W minus Z is strictly less than R, right? Is a subset of U. Right, so what's the picture for that? Basically, the picture for that is typically U would be some kind of blob, some kind of subset of the complex plane that sort of is missing its boundary, right? And we're saying that, so this set is open if whatever Z I can pick in the set, that's the set U, I can find a ball of some potentially small but positive radius, which is completely contained within the set, right? Yeah, that's it. So yeah, so essentially like this Z is really contained. It's really kind of surrounded by the set. It's kind of it's got a padding. Um, yeah. If I had some of the boundary was included, right, then that wouldn't be open because I could pick a point on the boundary, and then however small I make a ball around that point, it will always intersect the outside, right? Okay, that's the intuition. All right. Okay. So we have a U1 and U2 are open. So let U1, U2 in C be open. Always just start, but doing a direct proof, just kind of stating your starting assumptions. Okay. So what can we do? Uh, Simply kind of, well, not for now. For now, let's leave it at that, and let's focus on the goal. So we want to show that U1 union U2 is open. So to show that U1 union U2 is open, then we need to start with an arbitrary Z in the union. So let Z be uh, in the union. Okay. Mm, okay. And we need to show there exists a ball which is contained within it. There exists a ball centered around Z contained within the union. So um, well, we know U1 and U2 are open, so we know that if Z is in one of these, then we can find a ball around it, which is contained within, U1 or U2, whatever it may be. And if it's contained in U1 or U2, then it's contained in the union. So that's pretty much, you know, what we have. So, well, since it's in the union, it's in one of those, Z is in one of those two sets, right? So literally by definition, Z is in U1 or Z is in U2. If Z is in U1, there exists an R1 bigger than naught such that the ball of radius R1 centered around Z is inside U1, which of course would then be inside the union, right? In which case we're done. And if on the other hand, Z is in U2, then there exists an R2. The R2Z is in U2, which is also contained in a union. So in either case, there exists an R, greater than naught. R is equal to R1 or R is equal to R2, such that BRZ is contained in the union. Right? So U1 union U2 is open. We satisfy the definition. Okay, cool. All right, so question B. Let U be a finite subset of C. Show that 1. U is open if and only if U is empty. And 2, U is closed. Okay, and we have a hint. For 1, assume U is non-empty for a proof by contradiction. Okay. Yeah. So, or a proof by contrapositive, I suppose. So this is an if and only if statement we're trying to prove in 1. So we need to prove both directions. Let's do this direction first, right? So suppose U is empty and we'll prove it's open. Well, the thing is, then the empty set is automatically open. And U is open because essentially any condition on the open sets that start for all Z in the open set is going to be true because, well, there isn't a Z in the open set, right? So there's kind of no condition to check, right? Then U is open because, U equals empty set satisfies the definition of open set vacuously, we can call it. So that's okay, that's fine. Now for the this direction. So they talk about a contradiction, but I suppose like will well, would it be contradiction? So I guess we'll yeah, like we prove it by contrapositive, I suppose. So we can assume. So if we're trying to show U is open implies U is empty. The contrapositive of that is U is non-empty implies U is not open. Keeping in mind that U is finite. U is assumed to be finite throughout all of this. So if U is a finite non-empty subset, so why is it not open? Let's get a bit of intuition on that. So we're talking about a finite non-empty subset, right? So it's just a set of points in the plane. Um, well, yeah, I mean, of course, you know, it's not going to be open because clearly, if I pick just any Z in this set, then basically any ball is going to uh, any ball around it is going to sort of intersect its complement, right? Uh, yeah, and it seems super obvious, and I suppose like the way to make this precise is that you know because it's a finite set, then there is kind of a minimum distance from that point Z to the rest of the points in the set, if there are any. Um, so yeah, I mean, actually, oh yeah, I mean, I suppose, yeah, no, it's simpler than that. It's just that if if we assume that a ball is contained, I mean, if we assume a ball is contained within your set U, then obviously U must be infinite because it it contains the ball as a subset, and a ball of finite radius, positive finite, or rather positive radius, is infinite, right? In the at least in the for the complex numbers. Um uh so yeah, I suppose we prove this by could be contradiction, but more like contrapositive. We prove this by contrapositive. So suppose that U is non-empty, then uh, oh yeah, no, I guess it is contradiction. Sorry, my bad. Okay, yeah. So okay, we prove this by contradiction. So yeah, so because we're okay. So suppose that U is non-empty, and suppose okay, I guess I don't want to mix up. I don't want to confuse you and mix up contrapositive and contradiction. So we're proving the statement that way around. So U is open implies U is empty. Suppose that U is open, and for contradiction, that U is non-empty. Then we pick a Z in U, right? Which we can do because U is non-empty. And we assume that U is open for contradiction. So since U is open, there exists an R greater than naught such that BRZ is contained within U. However, um, you know, a ball of positive radius in the complex plane is infinite, right? So since it's a subset of U's, and U must be infinite, right? So uh, giving us a contradiction because we're assuming throughout that U is finite. Okay, got there in the end. Bit confusing, sorry. Okay, and then two, um, we'll prove that U is closed. So there's a lot of different uh, definitions for U being closed. I recall the one being the one I saw in the kind of um, you know, list of concepts for this course for this university is simply the following. Uh, U subset of C is closed simply means that the complement C the removed U is open. Okay. So I suppose that this picture still helps, right? Maybe I'll draw one more picture. So we've got U, a finite set, right? And then we've got a complement. So the complement is, you know, the white, right? The page. Um, so uh, let's see. Oh, let me use a blue just to differentiate. So what we'll need to show C without U is open is we'll need to, start with an arbitrary Z in the set and show that we can find a ball um, which is completely within this set. So we can find a ball which doesn't contain any of the points in the finite set U. Seems very believable. I mean, it seems obvious that we can do it, right? Um, but how do we actually do it? So this is where actually the kind of minimum distance thing applies, right? Because U is a finite set, um, there is a minimum distance from Z to the black points, and if we pick R to be less than that minimum distance, then the ball cannot contain any of those black points. So okay, so let Z be in the complement. Since U is finite, um, uh, the minimum um, distance between Z and let's call it U, where U is in U, right, is that's a positive number, right? Let me call that I don't know, little m. Sorry, it's a bit squeezed there. Yeah. So little m, right? So this minimum distance is greater than 0. So then I'll let R be little m over 2, right? Which is still going to be greater than 0 since m was strictly greater than 0. Then of course uh, uh, BRZ does not contain um, any of the points of U, right? Since uh, otherwise, otherwise the um, let's call it the points U in since otherwise the distance between U and Z would be strictly less than M, right? Which is obviously nonsense since M is the minimum, right? So anyway, yeah, it's pretty clear. So you know, BRZ is fully contained within the complement. Hence, um, the complement is open, so U is closed. It's falling off the page, but that's all. Right, 10 marks. Actually, I forgot where we started, but I think that was about 20 minutes. Let's see, 100 marks, 20 minutes, 200 minutes. We're going a bit slow, but I guess, yeah, you'd be going faster if you didn't have to explain everything.